Okay, I'll start now. So in the last lecture, we talked about all kinds of tools to do the simplification and to do the long proof. Today I will split my lecture into two parts. The first part is that I will introduce to you some of the tactics, some of specialized use of tactics in different circumstances, and another part is that I will show you some because do the mathematics is not only to prove the theorem. Another staple part is to do the construction of mathematical structures. And now today I will show you how exactly can you construct the mathematical structures in this in formalized language. It is very important if you want to do the formalization towards a very large project. For example, there's a theory or there's a kind of mathematical aspects you want to formalize. And today I will give you a glimpse how to do this stuff. So first I was going to introduce some of the more tactics to use when you do the proof. So I will create a new file for the convenience. First, we import mathlib. There are several kind of convenient tactics to fast simplify the statement when you do the proof. The first one, of course, is simp. Simp is what we use very often to do the theorem proving, but simp sometimes is not very powerful. For example, for this example, we can see from here. Here we can use simp to solve the goal, and simp is not enough. We want to see what exactly does simp do. So to achieve this, we can use simp question mark, and it will tell us to use the S0 to do this. So in this sense, what simp does is just it keep using the various simp theorems in the back end and use these theorems to rewrite your conjecture and finally try to close the goal or try to change your goal into a more simplified form. As we can see from this X0, that we can find that there's a simp annotation here, which means that this theorem can be used by the simp tactic. Lots of them have this simp decorator, and when you have simp, the simp tactic can use it. And so let's get back. But sometimes simp is not, it cannot do everything, right? Let's try another example, still in real number field. A very simple one. Let's just square equals to x multiply x. If we want to use simp here, we find that the simp will not work. This is not a good circumstances because this actually is very simple. There's also some more cases simp that cannot use to fast simplify your claim. For example, in this case, we want to just do a x plus x. We still want to use by simp. The simp is still not working. So how can we solve this? How can we mitigate this circumstance? We can define new simp lemmas, right? We can write our own and use the simp decorator. I will show you how to do this. The first is the first lemma I want to use is theorem x r, and x po 2 equals x multiply x by, here we use a different tactic to solve this. For example, linear race, we need to give a name. For example, my po 2 to do this. And we use linear race to close this goal. So after this, we can actually add a decorator called simp. So after this decorator, we can see that the theorem has had no change, but we found that here the simp tactic will work, because in the backend, you can find that it just use my po 2 this lemma to do this. So what's more, we can add a new theorem called my double. And it says that 2 multiplied x equals to x plus x. By still use another tactic. We can still linear race to solve this. Or of course, we can use other one. And by this, in this case, we get a new theorem, and we still use simp decorator. We find that the second one is also being solved. So that is how simp decorator works. So what's more, simp tactic can also recursively apply the simp lemmas, your set of simp lemmas, and try to make the claim more simple. We make the claim simpler. For example, I will use a more complicated proof, more complicated goal. For example, let's just add them together. Maybe 2 minus 2 multiply x squared equals to x multiply x and x squared equals by simp. So this will help us solve the goal. But however, if we cancel any one of these simp decorator, this will not work, because it's recursively use our simp lemma set to finish this case. So sometimes you found that, especially when you do a kind of new aspects in Lean that barely no one has formalized, and you find that simp is not very useful, you can use in this manner to make your simp tactic more powerful. So this is how simp work. And other thing that I have demonstrated previously, I will just show you how to do this. Not this one. This one. The second tactic I want to introduce is linear race. So you will see linear race in the REPL or in the mathlib from time to time, but it is actually a shorthand for linear inequality arithmetics. You can also solve the equality equation, but in the same algorithm. What it does is just use the very basic rule set to try to just in the inequality case, it try to find the counter example in the inequality. If in the inverse, for example, is greater than, and if it can find a counter example in the inverse way, for example, less or equal than, then you can use this property to solve the problem. So we still use this inequality example. We find that we use linear race, and it can find a counterexample to solve this claim. The difference is that because it uses the counterexample in the back end, it's type correct, but you cannot get what it actually does. You can just use the linear itself. It does you will not know what exactly lemmas and theorems it uses. And the third one is the norm noun. Norm noun is sometimes works similar to linear race, but it does a difference in the back end. It is more straightforward. It's just use numerous amount of theorems and lemmas to try to simplify these several operators into its normal form. Just now it includes add, subtraction, and multiplication and inverse in common number fields. Common number fields means several number fields listed below. Maybe there's a complex, real, natural number, integers, and rational number, I believe. Yeah, these five number fields. In these five number fields, it can normalize the formula and try to solve it. So this is how norm do. We can also use this example. We found that after norm, we just close the goal. So the difference between norm and linearis, the difference between norm linearis and simp is that the norm does not need to close the goal. If it fails to solve the goal, you can just use other tactic later on. But linearis, if linearis does not solve the goal, it will just fail, and you cannot use this tactic. So in the next example, in the next tactic I was showing is T-auto. The T-auto is a shorthand for tautology. So sometimes you will have trouble to construct to give proof to a very complex logic connectors, for example, or and you found that maybe each of the proposition is true. This is just exactly the tautology definitions in mathematical logic. So if you're convinced that each of your proposition is true, and in its trivial case, you can use T-auto to do this. Let me use another example. Let me double check screen sharing. Okay. So here is that we know x is larger than 0, and we know because x is larger than 0, x must not equal to 0, and we get this is true and this may be true. So in this tautology, it is exactly the tautology. So we can use T-auto to solve this. So traditionally, how should we do this? We use maybe first left, right, to solve the left-hand side and use constructors. And we found that the first case is just what we want. We use exact expose. And the second one, maybe we use simp, not simp. Let's see, maybe exact expose dot ne. Okay, it's dot ne prime. This means you can derive not equal from the less than. And here we get the proof. I found that from that we can see that each part of the proof is very simple, maybe just one line. And in this case, you can use T-auto. Use T-auto to solve this. Maybe we try a more complex connectors. Maybe we know P. We know X R. We have still expose X larger than 0. Maybe we have more connectors larger than 0 and larger than 2 or larger than 2 or X smaller than 0. And in this way, we can still use tautology to do this. Yeah. So if you encounter with especially when you deal with finite cases, for example, you want to enumerate many elements in a finite set, you can use and eventually we'll get so many justifications connected by logic connectors. And in this case, you can use TAuto to solve it very fast. So yeah, it's true. It's true. It is just a propositional logic. And so I'm going to introduce the next tactic. The next tactic is Omega. Omega is a comparably new tactic in Lean, but if you actually do proof, if you have deal with your problems, you'll find that you will spend lots of time on solving inequality and inequalities in natural number when you do the proof. So Omega is such kind of tactic. It can help you to solve especially problems on natural number and integer numbers. But to this extent, in current period, a Lean community is working on this tactic to make it more stronger. But now it can only solve very simple natural number problems. And so these two examples illustrated the natural number problems. And finally, should be the most powerful tactics in Lean is ESOP. The ESOP is like it just try all the kind of type correct tactics and try to use the tree search to close the goal, because you can expect that each kind of in each time you apply a tactic, it just change the goal to a different state. And if you imagine all the tactics at edge and all the proof state as nodes, you can find that to find a proof, it is just to navigate in a proof tree and find a path connected from your initial declaration to no goals. So ESOP does this automatically for you. It uses exhaustive search to try to find the proof, but in most cases, it does not work well. But for maybe 3 lines or 4 lines proof, it has a very good performance. So you're encouraged to try this in your proof or in your homework. So the next is the main goal or main topic today, which is structures and type classes. I will write in this new file. So this demonstrated how you can create new mathematical objects in Lean. So let's start with a very simple one. For example, you want to create a 2D point, a set of a type of 2D points. You can use this structure keyword. For example, it's point. You can specialize what exactly is each axis. For example, the type alpha. It is type U, which means it can be real number, complex number, any number you want. So how do we define each one? We define X is of type alpha, Y is also of type alpha. So here you have a very simple structure. It is actually a 2D points, 2-dimensional points in a 2-dimensional space. And how can you initialize this? How can you create a structure of this type, which is we use definition, my point, 2. The entry is also, all of them is 2. So when we do the initialization of the structure, we need to tell it what is exactly is alpha. Here we specify it to be R, which means each of number is of real number. So we can use this to specialize to tell this is a point. This is a point in the R2 space. Yes, so this is a very simple case, and we can also define some kind of addition to on this space. We'll skip this part and we'll demonstrate how you can define something more complex in Lean. It turns out that you can specify a type even specify variables in the structure. Another thing you can specify in this structure is that you can even make a proposition to be a member of this structure. For example, there's a more complex one. We call it positive point. Oh, it's shown here. Maybe I need to turn. For example, we want each of the entries Q is in the rational number. And in addition to this, we supply two proofs, two propositions for this structure. The first one is X is a positive number, Y is also a positive number. So how is this useful? Which means that when you try to define a structure of this, when you define object of this structure, not only you need to specify the not only you need to specify the variable, you need to prove that the variable is actually what you want. In this case, we still provide each one. Sorry. X equals 1, Y equals 2. It has to, and Lin will complain that something is missing because you haven't proved everything. So now we prove that first claim, we can also enter the tactic mode to do this, which is just a very simple numerical numerical computation. We can use simp to do this. And finally, another proof is Y pose. We do it in the same manner. And now we have create an object of this structure. So it has two benefits in computer science, which means that it automatically checks that your input is validated. Your input is valid. It will reduce the safety concern. But in mathematics, how is this useful? How is it useful? This proposition declaration allows you to create new mathematical objects out of just a simple variable, which means you have members in this structure. You have axioms. You need these members to obey, and then you will have a mathematical structure. So we can look back in this file. Yeah, first we also have a addition of points definition, which means this function adds two positive points and get a new positive point. And to get a new positive point, we need to do first specify what is the actually addition procedure, which x is just xy is just the addition of the respective entry. And we need to prove that actually one positive number plus another positive number still yields a positive number. So here we get a second usage of linear arrays. You can actually specify what lemmas or what theorems you want to use in the linear arrays by this squared bracket. So after this notation, the linear arrays knows that it can use these two notation to do the simplification, and it will help you to finish this code. So after this, we want to I have said that you can actually define mathematical structures out of this structure definition. So let's try a most basic one, which is the group structure. So I believe first I will, in case some people are not familiar with group, I will demonstrate what is a group. So traditionally, to let a set or letter or typing link to be a group, we'll actually specify this kind of thing. This is identity element, and there's a modification in the structure, and there's a three three axioms to follow. You need to specify these three axioms. The first one is that the multiplication associativity, which means for arbitrary x, y, z in G, you need to have x multiply y. This is just associativity. This is the first axiom. And second one you will see in most the algebra textbook is that for arbitrary x in G, you will find an element. We'll call it an identity element. Exists E in G such that E multiply x equals x and x multiply E equals to x, which means that formally, which means that this E is both a left identity and a right identity. This is the definition of the identity. And the third one you need to follow is that you need the existence of inverse operation. For arbitrary x in G, there exists a y in G. We call it x inverse, which is x multiply y equals E and y multiply x equals E. In the same manner, we call that y is both the left inverse and the left inverse and the right inverse of x, which finished the definition of a group. So anything that satisfies these three axioms will be a group. So of course we can actually realize this in Ling, but which means that you need to realize all the condition here, And the first one is the left identity, right identity, left inverse and right inverse. There's 5 of them, which means you need to prove 5 axioms whenever you want to create a group. So a natural problem is that can this set of axioms to be reduced to less axioms, so that you maybe some axioms can derive into each other. This may be not a trivial question in mathematics, but in Ling, if you can reduce an axioms or 2 axioms, it will save you lots of effort when you need to prove new thing. So it turns out that actually mathematically, this right identity and this right inverse can be automated, because if once you have the left identity, you can actually derive into the right identity, and once you have the left inverse, you can derive the existence of the right inverse. I will say that this is a basic but non-trivial problem. Mainly actually, it comes to me very seriously until I started programming Ling. So I want to share this experience to you, how you can reduce the axioms in the group. So we can see that in this definition, it's a very simple definition of group. We first have a multiplication, and second, we have an identity element. Of course, you can omit this identity element, but otherwise you need to pick the existence of this identity from this claim. So I use a new symbol to stand for the identity. So here we just specify the left identity and left inverse. So now next we need to use the theorem of this. We can write theorems of this structure to derive the right inverse. So actually, I want to demonstrate to you how we use this structure to prove new theorems. So I will copy this to a new file. So this is my group. Now you want to prove this. You have a multiplication. So, so first I will demonstrate how can you prove prove it mathematically. Actually, you have we can identify that if you have this, if you have this, if you have left inverse implies right inverse, and actually you can directly derive this left identity if equals right identity. I will demonstrate in Ling later, but now we focus on the proof of this this sentence. What we actually want to prove is that for arbitrary x in G, there exists y in G such that y multiply x equals e. And we want to derive that also with the same y, we have x multiply y equals e. It's a little bit tricky, but I will show you. We want to prove that this x multiply x multiply y equals e, because the property of left inverse arbitrary x, we can find the new element z to be the inverse of x multiply y. This z is due to this statement. Because x is the universal quantifier, so you can specify x to be x multiplied y, and you will have a z here, which is a left inverse of this of the element. And the first thing you do is you apply the left identity. To be serious, we only have the left identity here. So when we can write y to be 1 multiply y equals e, and further we write 1 to be y multiply x, because we already have this left inverse. So we write 1 to be y multiply x multiply y equals e. And then we find that we can just recursively use the associativity of this multiplication, which is guaranteed by the first axiom. So now we can just rearrange the bracket. We'll have this y equals e. And in the first case, we already have this z multiply x multiply y equals e. So we can just substitute it into e equal x multiply y equals e. And in the last circumstance, in the last equality, we find that actually we already have the left identity. Left identity multiply arbitrary x equals x to itself. So this will yield us x multiply x equals to identity. So here is how we start from y multiply x equals to identity and derive x multiply y equals identity. So in Ling, we do it the same way. So to save the time, I won't prove it exactly this. So we first have this. We first have use obtain to destruct the existing quantifier, and we get hy. We get the left inverse we want. And there's actually two things we want to prove. The first is that the first is just the left inverse itself. The second is the right inverse, which makes sure with this statement has make sure that left inverse equals right inverse. And we just repeat the procedure, and we will get this statement just the same as I demonstrate here. And we can keep rewrite keep using the associativity of the multiplication, and finally, we will get what we want in Ling. So this is a simple demonstration of how you can use a set of minimal lemmas on a structure, and you use the additional theorem to derive more lemmas, more consequence of these axioms, and then start from this, you actually construct a theory in mathematics. Actually, everything in the group theory you can derive is derivable from this my group structure. So this is how you can define mathematical theory. Basically, procedure you define mathematical structure and theory in Ling. And the second proof is that this proves the just thing I said before is the left identity equals right identity. And from now on, we will have a completely classical definition of group theory of group using just 3 axioms in my group. So now we already have the structures. So another thing is that we also want to define functions and some properties on these structures when we realize our structure. For example, we sometimes want to specify some. For example, in this case, my group Z integer is actually a group. So let's prove this. So we want to say that integer is actually a group. So in the same manner, actually exactly same with the way you define points. So first we specify what is the multiplication in these integers, which is addition, because in integers it only constitutes a group with respect to the addition. And secondly, you specify what is an identity element, which is 0. And now you prove the 3 axioms that a group must satisfy. So for the associative, we can use actually an already existed claim in integers, which is add associativity. And for the left ID, we can use tactic mode to see what we actually want to prove. We can intro x. We can see that it's actually 0 at x equal to x, which is a very simple lemmas in Z. We can use exact 0 at x. This will finish it for us. So for the left inverse, is by intro x, and now we need to use this. We need to pick y to be the inverse of x, which is with respect to addition is just negative of x. So then finally we need to prove the negative at x equals 0. Let's try simp. So simp works. So in the backend it uses the neg add cancel. This lemma should do. So now we have already supplied a proof that the integers is actually a group. So the cumbersome thing come after. The nasty and cumbersome thing comes after, because when we use structures, every time we want to define some actions on the group, we first need to prove that this type is actually a group. For example, in this square operation, we first say alpha is a group, and we want to define a square action on the group, which is just x multiply x. And when we want to realize, when we want to compute this thing on integers, we find that we first need to supply a proof that this integer is a group, then we can do this computation. So it is very nasty because we don't want to we want to prove it once, and in other case we want to link to automatically determine what is the fact behind. So here the structure is not so useful. So we use a strengthened version or improved version of structure, which is called class. So class is exactly the same same syntax and same usage with structure. You can just directly change structure to class. You can compare this to stuff. We change structure to class. So after this, if you can use instance to specify that the integers are a group, we use this structure definition, the class definition. And after you define here, after you make this definition, it's like you register this class into the link itself, and link will have a table. You know, is a group. It's a very global table, so you can access it anywhere in link. And when you need to fill in something that is my group class, and link will deduct for you in the backend. So we can now redefine this this square operation. I see that this will become an implicit instance. When we want to specify an instance or specify a type class, we use this square bracket. So after we want to define this operation, link in the backend will know this Z is my group class. This is deduced in the backend of link. So in this case, we don't need to actually specify to give supply a proof here, and link will know the proof is actually here. It will so this is how type class work. Basically in the same with structure, but with auto deduction. So that's for the all for the type class. And since we already mentioned the type class, we want to mention speak some more thing about this type class thing. So in the programming context, the type class is actually used to realize something called a polymorphism in programming side, which means you can apply a same function to different type, to different structure, and in the proof which is this instance, you give the detailed realization of each operation. For example, this toString things, what it does is to convert any structure in ling into a string, into a character list, into a string, so that we can display very easily. So we can find that it's just a type U, and if we get access to the method, we find that it's any structure to a string. However, if you want to use this function, you need to have a toString type class. So for all the class we mentioned before, we can give a proof, or we can give a realization of this toString instance. For example, for the point, which is as I programmed, it will show what is X and what is Y, and this is for different type. And for the positive point, we can show that we can still extract what is X, what is Y. This string is completely customizable. It will define different behavior with respect to a different structure. So we can also define the toString operator with my group. But in my group, there's nothing to show because the group is not we cannot easily print elements in an abstract group. So next we can actually compute. We can use this toString to show what each thing actually is. We can just see from the output that it works fine. So in this case, we use the same function applied onto completely different structures, include math structures and programmable structures. And in this case, you will get more flexibility. We will need to define different functions, or you want to realize different functions in your program. And this is the second thing. And the last thing I want to mention today is that how can you organize a file from beginning? How can you make your code more neat, more fit for the math.lib style? So I will copy this, since the time is limited, I will copy this into a new file. So here, what we actually does is that we define something called a series, and on top of series, we define something called an arithmetic progression, which is just each difference between the entry of consecutive elements is the same, which means it's like this. So how we define this property? On top of this is the function which maps from the natural number to any type, which I demonstrated in the first lecture. And on top of this, there's a additional property that this function need to satisfy, which is this. So that in this case, anywhere we supply this proof, the link will know we are talking about arithmetic progression. So how can we organize our file? First, we need to prove some kind of properties and theorems in this structure in this class. So we first use a namespace to limit the scope of our code lemmas. So in this namespace, we can define various variables, various local variables, so that all the lemmas can use. For example, in this theorem, it says common diff, which means all the differentiation actually refer to the first difference. The first difference, A1 subtracted by A0. Also have a notation, which match the style we're talking about in normal mathematics, which is D to denote the difference. So we can supply a proof that for arbitrary difference equals to D, and we can also prove the formula for any elements in this series, which is like this. Note here I use a decimal instead of multiplication because we let this this series to be arbitrary type, as long as this type has the additive common group. So in this case, we will not have the multiplication, but the addition. So this decimal means that just n copy of addition. So if you have a ring or you have a field, this operation, decimal operation, just equal to the multiplication. So now we can use our definition, use our notation to very decently prove our general formula for arithmetic progression. And in addition to this, we can also use local notations to show the summation of this series. Oh, I will delete this line. And of course, we can use the mathematical induction to prove the sum formula. For our this arithmetic progression. I didn't prove it all because the later on it's just arithmetic. So after that, you actually get a very complete statement of a structure, the type class, and the rules it need to obey, and some properties it has. So after in other place or in other file, anywhere we open this arithmetic progression, and we can specify a new series, and we can immediately prove that this series is a arithmetic progression. And then after that, we can get access to all the properties and lemmas that this structure have. So to be short, if you want to prove something new, or if you want to prove something that doesn't have in MathLib, you can use these very simplified manners to define new structures or new properties with respect to your structures. And you can, it's like building blocks. You will have so many of useful blocks. After combining this block, you can make a very long or very complex proof easier or faster. So that is how you do it. So I think the time is up. So I introduced briefly about how you can use various kind of different tactics, and how you can, in addition to just prove everything, how you can just initialize or construct various structure and prove theorems and properties on top of these structures, and together you will get a new theorem or more complex proof in mathematics or in formalized mathematics. Okay, that's all for today.